Hello, and welcome to this introductory video on equipotential lines or equipotential surfaces, depending upon the number of dimensions in the problem that you're actually investigating. So in this video, we're going to motivate the idea of what equipotential lines and surfaces are, what they represent, and also hopefully give you some idea of why they are important if you're trying to figure out something about the dynamics of your situation. In order to talk about that dynamics, what we realize is that fundamentally, again, as in previous videos, the important thing in terms of what's going on is the change in the potential energy. Okay? And therefore, we can substitute in the fact that that's really just looking at the change in what we've defined as the potential. Remember, the potential is just the potential energy divided by the charge. So since that's the fundamental thing, we want to know, is it changing? Because if it decreases, then we know that we've sped up, and if it increases, we've slowed down, that sort of thing. That's the fundamental thing of interest. It would be nice if we could quickly represent this in some way, shape, or form on diagrams. Just like we've got diagrams to show the electric field of a situation, and we know that it's stronger where the lines are denser, and that it gets weaker as the lines spread out, and things like that, and it conveys the direction. We would like to know something about how the potential is changing. Would like a nice graphical representation of that as well. So let's think about that a bit, because of course this is going to be very useful to us to define regions where the potential does not actually change, because then we know that we can sort of move along those without speeding up or slowing down, for instance. Okay, so we're going to denote these by equipotential lines and surfaces. So let's think about having a charge. Okay, we can draw in our electric field. So the electric field line indicates the direction something, which is particularly in this case a positive charge, would move. So the field lines point away from this positive charge. We've seen this several times before, so I'm not drawing anything new there. But why does something move? Well, it's moving because the energy here is high. If I put a positive charge here, it's got a lot of potential energy. It's going to want to move away, and it'll speed up as it gets pushed away from this other charge. So the energy is high closer in and weaker further out. And basically what's really going on is that a particle, when placed in some region with some energy, tries to find a minimum energy state. So it'll move towards lower potential. So we know that somehow here we have lower potential, and somehow close in we've got a higher potential. But exactly where does that potential stay equal? Now, it's probably not too much of a stretch to suggest that it's going to be a little circle. So the potential at the same distance from the charge should be the same. So as I go around there, I'd probably get the same potential. I think that conceptually makes perfect sense, but let's just talk about it a little bit in terms of what these things are representing. So remember that our field lines are really just representing basically what the electric field is doing, because it's tangent to the line at the point. So right here we have a force which is trying to push us, actually everywhere we've got a force trying to push us radially outward. So that's our forces. They're just trying to push us radially outward. Okay. So what about the direction perpendicular to the field line? There's no force in that direction. The force is along the field line. There is no perpendicular component of the force. If there's no force in the direction perpendicular, well, that's exactly the sort of thing that we're looking for. If there's no force, then the energy is not changing, because the force will not do any work as I move perpendicular to the force. Right? Work is force dot the displacement, or force times cosine of the angle between the displacement and the force times the displacement. So there's no work being done if I move perpendicular. And if there's no work being done, then there's no change in the potential energy. And if there's no change in the potential energy, then there's no change in the potential. And so if I'm moving perpendicular to the lines, and the lines are always radial, then of course I must be drawing a circle. Okay, so now we've convinced ourselves that perpendicular to the field line, the potential is not changing, and therefore this circle traces a region where, indeed, the potential is the same, i.e. equal along that circle. Right? And if this was a three-dimensional thing, then instead of a circle, I'd be drawing a sphere, completely encasing this thing with a nice fixed radius, and the potential will be the same everywhere on that sphere, because each way as I'm trying to move along that sphere, I'm always moving perpendicular to the field lines. So the equipotential line or surface is indeed given by this prescription that you just draw them as perpendicular to the field line at every point. By going perpendicular to them, you're guaranteeing the potential isn't changing, so you've got an equipotential line or surface. So what that means is, if you move between any equipotential surfaces, so maybe another one out here, which is V2, and this one is V1, and we know that V2 is less than V1, then we could ask, given an electron that starts here, a nice big one, and it ends up, I don't know, here. Doesn't matter how we got there. We know the initial condition, we had a potential of V1. The final, we have potential of V2. Therefore, if we take that, all right, that is a joule per coulomb, it's a volt. So if we multiply that by the charge that we moved, I said that was an electron, so in this case it would be the charge of an electron, then that would be the change in potential energy. And that would equal, right, the change in kinetic energy if we're conserving energy. So if there's no non-conservative stuff happening, then we know that that's a change in kinetic energy, and we can talk about how fast we're moving.